Hello, welcome to Deterministic Optimization. My name is Shabir Ahmed. I'm one of the co-instructors of this course. In this lesson, we'll continue our review of some mathematical concepts required for optimization. In particular, we are going to recall some basic concepts for multivariate functions. Let's get started. So we are interested in functions which take on a value from a domain. This is called the domain of the function, D. That's a function f, which takes a value from a domain and produces a number, r, which is called the range of the function. So we are interested in multivariate real-valued functions whose arguments are vectors. So in that case, the domain of the function is a subset of the n-dimensional real space. That's what this means. And whose range is a real number, r. This range is a subset of the real line. So the argument is a vector in general, and the output of the function is a number. Right? So here's a little pictorial representation. So this is a function. It has a domain and it has a range. The domain is the set of values for which the function is defined, and the range is the set of values for which of the output of the function. So here are some examples. For example, if you are interested in the function f of x, which returns the sum of the absolute values of the components of the vector x. Right? So that's what this means. Here the domain is Rn because the function is defined for all n-dimensional vectors, and the output of the range of the functions is the non-negative real numbers because we are summing up the absolute values, so therefore they are all non-negative. Another example, this is a one-dimensional function of a single variable. Here we have f of x is equal to log of x. In this case, the domain of the function is the positive real line. So R++ means is the set of positive numbers, real numbers, and because the log is defined only for positive values, and the range of this function is just the real numbers, right? So all real numbers. So let's define the notion of continuity of a function. So a function is continuous at a point x0, a point which is in the domain, obviously, if you take any sequence of points whose limit point is the point that we're interested in. So here we have a sequence x superscript I, such that the limiting value of this sequence is x0, then it holds that the limit of these function values is equal to the function value at the limit. That's the definition of continuity, a mathematical definition. So a function is continuous if it is continuous at every point. So this is continuity at a particular point. If the function is continuous everywhere, then it is called a continuous function. So roughly, this is a mathematical definition, but roughly, essentially, a function is continuous. It means that it does not have any jumps. So for example, here, this function has a jump at the point 1, right? So at the point 1, the function is this value, but if you move a little bit away from point 1, the function takes a value of here. So this is a discontinuous function, whereas this function is continuous at 1. Now, recall the definition of differentiability of a function. So for a function of a single variable, a univariate function, where the domain is just the real numbers, set of real numbers, not vectors, we say that it is differentiable at a point x0 if its derivative exists. Now, what is the derivative at x0? It's essentially kind of the limiting value of the slopes of the function. Remember this from basic calculus. So this is the function value at x0 plus h minus the function value at x0 divided by h as h goes to 0. Right? So this is the slope of the function, and essentially we are interested in the limiting value of these slopes. How do we extend this definition to multivariate function? We say that a function, multivariate function, meaning that a function of vectors are in n-dimensional vectors, is differentiable at a point x0 if all the partial derivatives exist. So a partial derivative means that you basically take the derivative of the function with respect to one of the arguments of the function. So here, for example, you are taking the partial derivative with respect to the jth component. So we look at f of x0 plus h times e to the power j. Remember that ej is a vector of zeros with a 1 in the jth position. So in other words, x0 plus hej means that we are just adding h to the jth position of x0 minus f of x0 divided by h. So this is the partial derivative with respect to the jth component. If this partial derivative exists for all j, and they are continuous, then we say that this multivariate function is differentiable. A function is differentiable if it is differentiable at every point, not that particular point x0, and the gradient vector at a particular point x0 is essentially the vector of the n partial derivatives. right? So we just described what the partial derivatives are. Essentially, if you take this partial derivative and write it out as a vector by each component, so this is the vector, then this is called the gradient vector. So for example, just to give you a more example about differentiability, the function absolute value of x is not differentiable at x0. And the gradient of this two-dimensional function, which is x squared plus y, at 1, 0 is, if you evaluate the gradient, you're going to get, so if I take the partial derivative, let me write this down over here. So the gradient of xy, this vector, is going to be, this gradient is 2x when you take the partial derivative with respect to x, and when we take the partial derivative with respect to y is 1. So that's 2x plus 2x is the first component, 1 is the second component. If we evaluate this partial derivative at the point 1, 0, we're going to get 2 times 1, 2. 1 is the second component. Remember, the y does not matter here, so this is the gradient at the point 1, 0. Okay. What is the Hessian matrix? So a Hessian with a twice differentiable function at a point x0 is an n by n matrix of the second order partial derivatives. So in other words, so this is the Hessian matrix. So we take the first partial derivative and take its derivative again with respect to x1. We take the first partial derivative, take its derivative with respect to x2. That's the second element, and so on. And we produce this n by n matrix that is called the Hessian. Now let's talk about Taylor's approximation. So if I give you a function which is n-dimensional, which takes an argument which is an n-dimensional vector and is differentiable, and a particular point x0 in its domain, Rn, then the first order Taylor's approximation of this function at x0 is essentially given by a linear approximation, which is obtained by the function value at x0 plus the gradient of the function, scalar product with the difference of a point x from x0. Right? So this is the usual first order approximation. And the second order Taylor's approximation is obtained by adding the second order term, where we basically take half of the difference from the point x to x0 times the Hessian matrix post multiplied by the difference vector x minus x0. This is called the second order Taylor's approximation. Here is an example of the first and second order Taylor's approximations of functions. So here is my function f of x, which is 1 plus x minus x cubed. So this is an example in a single dimension. So this blue curve is our function. What is the derivative of this function? At the derivative, if you take the derivative of this, take the derivative of 1, you get 0. Derivative of x is 1 minus 3x squared. That's the first derivative. What is the second derivative? We take the derivative of this, again with respect to x. You get minus 6x. And the first order Taylor's approximation is something that you should verify at the point negative 0.5, which means at this point, is, if you plug into the formula that I wrote in the previous page, would be 0.25x plus 0.75, which gives you this dotted line. So the first order Taylor's approximation of a function is a linear approximation of this function at the point, which is exact at the point that we are deriving this approximation. In this particular example, this is the point negative 0.5. The second order Taylor's approximation at the same point is a quadratic approximation of the function. This is this red dotted line, and it is obtained by 1.5x squared plus 1.7x plus 1.125. Again, you should verify by plugging into these expressions, and the point x to negative 0.5 into the formula that I wrote in the previous page. Okay, so let's summarize. So what we have done is just reviewed some basic concepts about functions, in particular continuity and differentiability functions, as well as its first and second order Taylor's approximations. Make sure that you verify the example that I presented in the last slide so that you are able to understand how to construct Taylor's approximations of differentiable functions. See you in the next lesson.